let's start. Like somebody said, I'm from Kuopio. Ari Paakkonen. I'm a medical physicist by profession. I've been working in the Kuopio University Hospital and in the Department of Clinical Neurophysiology since 1984, so quite a long time. And I've been doing event-related potentials, I think a little bit more than 20 years now, so I have some experience on that, but not very much on their use in linguistics, because this was my experience started about 5 years ago when we didn't have the University of Eastern Finland then. We had Kuopio University and Joensuu University, and then these universities decided that, or maybe the state of Finland decided that there could be a single university, and there was a so-called union university enterprise where the universities were looking for different places of collaboration, and one of those was then collaboration between the linguistics department of Joensuu and the neurology department of Kuopio University. And that's how it started, and then I have been collaborating with Santeri since then, and that's the reason why I'm here. Because if we hadn't had that collaboration, then I wouldn't be here. But it's nice to be here. Also working with Jussi, of course, because Jussi was actually one of the initiators of this Union University enterprise. If I'm translating it correctly, probably not, but something like that it was. Okay.
Well, my modesty sort of forbids me to say anything.
Okay. Right. Let's go to the subject, event-related potentials. I think most of you have heard about those. Some of you may have done some studies on that. So I actually start from the bottom. I'm first defining what they are. And for that, I have to explain a bit about EEG recording, then something about evoked potentials, and what is the difference between evoked potentials and event-related potentials. Then I'm telling you very briefly about properties of event-related potentials, and then some examples, let's say about the historical examples. And then I'm speaking a little bit about ERPs in linguistics. Okay.
Sorry, could you please use the microphone so that everybody could hear you?
Ah, this one.
Yeah, thank you.
Okay, I'll take that. Is it better now? Okay. So event-related potential recording is one of the major tools of psychophysiology. And you probably know what psychophysiology is, but that it's not very easy to define what it is and where it belongs, but you can say that it is a branch of cognitive neuroscience. And it studies the cognitive functions by measuring any physiological changes, almost any physiological changes can be used, that are produced by a psychic event. And the most typical physiological changes are changes in EEG or changes in heart rate, but also, for example, changes in sweating and things like that. Almost anything can be used. What is EEG then, or electroencephalography? It's the bioelectric activity of the brain that is recorded from the scalp, usually from the scalp. When you are doing psychophysical experiment, you are recording from the scalp. In the hospital, we are recording from the top of the cortex, or even we go inside the cortex to do the recording, but it's not, there are different recordings then. So, from the scalp, you are recording from the scalp, and you are using electrodes, of course, to record. And they mainly are postsynaptic potentials. There may be some slow potential changes, but they are not action potentials. So it's different from the nervous signals that we are recording from the peripheral parts of the body. Then we are mostly recording action potentials. But in the brain, they are postsynaptic potentials. And there has to be a very large number of neurons that function simultaneously and have the same orientation, so that we can see it from the or on the scalp. And one of the problems is that the scalp recorded signals are firstly they are attenuated, and even worse is that they are smeared by the many layers of tissue, which is the main parts are scalp, skull, and the cerebrospinal fluid. So those are between the source of the EEG, which means the currents there in the brain, and then the electrodes. This is a picture of how it goes. Let's see. No, it's too difficult to use the cursor on that one. But you can see that there is a scalp layer on top, then skull, and then there are different layers, which most important is the...
Don't you have a laser beam on the remote?
This one?
Yeah, does it have a laser? Don't point at us.
I don't use it. I don't know.
Okay.
I don't need that so many times that I think I can explain it. So actually there's a cerebrospinal fluid, in that picture mainly in the subarachnoid space then. And that means that we have there a layer that is very good conductor, so that the currents flow easily there. Then we have the skull layer, which actually is an insulator. So almost no currents can go through that. And on top of the skull we have the scalp, which is also a very good conductor. And together this means that if something happens inside the skull, and we are trying to measure it from the skull, it's very hard to tell where it actually happens. If there is or when there is a source of electricity inside the skull. And this is the difference between, for example, EEG, where it is difficult, or MEG, where it's much easier to see it from the raw data. In EEG, you can do source localization, then it gets easier, but still it's quite difficult usually to. And you have to have a large number of channels, meaning a large number of electrodes that you can then like to solve the problem where the source of these potentials that you are recording, where the source in the brain is. So it's not simple. So we are recording from the scalp with electrodes, and the usual type of electrodes is so-called silver chloride electrodes. That is the best electrode for the recordings, because it's all its properties are actually very good for the recording. Main thing is the chloride ion, and all good electrodes usually they have chloride ion, because our chloride, our body is very, very abundant of chloride. And that means when we are using an electrode that has a salt, like in this one, this silver chloride, chloride is one part, then it actually doesn't interfere very much. Even if there is a changes in the recording, the changes are very small compared to the total chloride content of the body, meaning that it doesn't interfere by itself. And it doesn't produce any double layers, which are a problem if you are doing recordings with electrodes like, for example, golden electrodes or pure silver electrodes, and they don't behave as well as this electrode. The frequency range usually that you are recording is from 0.3 Hz to 70. This is the classical EEG frequency range that you are using in the clinic when you are doing the recording. But of course there are other frequencies like higher frequencies. For example, when we are doing epilepsy recordings, we are sometimes recording very much higher frequencies, but there's something that can happen, especially if we are recording from inside the brain. And in small children, like in preterm babies, there's a lot of information below that 1.3 Hz, so very slow frequency EEG, because the brain is not nearly ready, and then there is more information in low frequencies. And usually you need at least 20 electrodes to do even a clinical recording. In an experimental setup you probably need to have much more. And you also usually are also recording ECG or the electrocardiogram and EOG or electrooculogram, and that's important because you have to know how the subject or the patient is blinking and what are the eye movements, because they affect the signal quite a lot, especially in ERPs. They're very important to record.
Procedural question.
Yeah.
Since you don't have a handout, would it be arranged so that you send these slides via email to each participant? So you don't have to write down everything?
It's possible, yes.
Okay.
Of course you don't have to write down it. It's very difficult. Because, and also, I think at some places I'm saying a lot more than it's on there.
They never learn.
They never, yeah, but some, because there are more than 20 of these people, and I think there are bits and bits and bits in different heads, and that's good. Not every person learns everything, but I think it's good that some people learn something.
You are an optimist.
Yeah, I'm an optimist, yes. So, that's at least 20 electrodes. And there is a typical system, which is called International 1020 system, which is described there. How we set the electrodes, because if we want to compare recordings between different laboratories, of course you have to have a sort of way of telling how and where these electrodes were. And that's how they are placed. I don't explain it in detail, but it's actually quite a good system. It's easy to start. You're recording first the center of the head, the CZ electrode there, and then start placing. That 10-20 comes from the percentages that you go over there. You see that CZ is on top of the head, then you go 20% up from the distance between this Naesian and Inian in your neck. 20% from CZ forward, you are getting this FZ which means that this is the frontal midline electrode. Z means midline, and on the right hemisphere, all the labels, the numbers are even numbers, and on the left side they are odd numbers. And that is how the labeling goes. But of course, if you want to have more electrodes, then you have to use a slightly different naming, and there are two, or at least two different ways of doing that. This is 10-10 system. There are some extras between those, what you have in this 10-20, and slightly different, slight additions to the naming, and then there are some that actually have different names in the 10-10, then 20, and then 10 system. But if you are, when you are doing these works, you know that happens. But it may sometimes be confusing if you don't know it. And now, of course, there are even, it is about 64 electrodes or 60 electrodes, but then you can have a setup where you have, for example, 226 electrodes recording, and then the naming is, then you can, I think it's simpler then to use just the numbers. Not so easy to, or not even try to name each of those separately. But it's important in the clinical recording. Also in the ERP, that you are reading from the, when you are reading the publications, then they're usually, the most typical names are CZ, the mid one, and then the frontal, and so, or then areas maybe that combine some electrodes. But it's easy to find out. If you want to know, then you can go to internet and search for this, for example, 10-20 system. Easy to find there. And the book there, Malmivo and Bloms, it's actually a book in the internet, so it's free to read. It's let's say it's heavily physical, but it has some good parts, very nice pictures, and so that you can look for that bioelectromagnetism. So one is Finnish author, the other one American, but a very nice web book. Okay, then we go to evoked potentials. Evoked potential is electric response in the nervous system that is elicited by a specific stimulus. And that's a fairly historical naming. And it's also, this cognitive evoked potential is also historical, because when people started to call the potentials that were related to analysis of the stimulus and affected by memory and expectation, attention, and so on, they started to name those as cognitive evoked potentials. Not so much used anymore, because this event-related potentials, or ERPs, has actually, it has become the standard naming. And it's a good name actually, because also you can call any kind of evoked potentials with the name of event-related potential. Even though in the clinic we still use the evoked potential name in many cases. Then we go to cognitive ERP waves and components, and it is assumed that if we have a single cognitive process, that it corresponds to a certain ERP component. It often does that. But it's not reversible. Because if we see a cognitive ERP wave, for example, any of the linguistic ERP waves that you may be reading about, they usually have a rise from a different processes. So there are several cognitive processes which may be related to perception and memory and attention, and these are running in the brain in parallel or in serial way or both. So that it's difficult to tell. In some sensory systems it's easier, for example in auditory systems it's easier to divide what happens first and what then. In visual systems it's much more difficult to tell how things go, and if you have a recording response it's more difficult to tell which one has happened first, even if you see the wave there somewhere. You can't be sure that something has started earlier than another wave. Then a few words about properties of ERPs, mainly with respect to recording and signal analysis. So the amplitudes are evoked potentials and even related potentials are very small. They are usually in the range of 0.1 microvolt, which is very small, to 20 microvolts. Some may be slightly bigger, but mostly that is the range. And that means that even the biggest of them are about the size as the smallest amplitudes in spontaneous EEG. And that means that averaging is necessary. You have to produce several stimuli and then average over the stimuli to get the result. Because when you are averaging, all the noise that is there fades away and you are seeing the signal, the real signal, better and better. Latency varies from 1 millisecond to about 1 second. Of course, there may be longer latencies, but then they are difficult. I think even 1 second is difficult because the brain works all the time. And we don't know when the time from the stimulus gets longer, it's more difficult to tell what the brain really does then. When it does the analysis of it, you define a task, and when it has done that part, for example, finding the pseudo words among the real words, when the brain has done the task, and it's difficult to tell what it actually does after that. And I think
is that for visual perception only? How about auditory and haptic?
Everything. No.
It's within that brain all the time.
Yeah, I think it's not. It's very dangerous to claim something that the long latencies. I think even anything that this is my opinion,
okay,
that anything that goes, for example, after maybe 800 milliseconds, it's very difficult to claim anything there, because it's very difficult to control the state of the brain. I don't know what. Maybe in linguistics, if you are doing like a sentence analysis, doing a part there, and then the sentence continues, then you know what goes on there. In that case, it might be possible. But for example, for one word, either written word or on the screen, or if you are hearing the word, then be suspicious if someone claims that there is something going on. And I think you should be suspicious. Like always, if you are reading a scientific paper, I think the good practice is to start. I usually start with, what is wrong with this? Why do they get this result? Then I try to see if there are any real mistakes. And if I can't find, then I think, oh, it really may be like that. Start with first looking the errors.
I would call that the mother-in-law attitude. Always suspect everybody.
Yeah. I think but with these papers it is good. Yeah. Okay. ERP is not completely deterministic. So, meaning that even if we produce the stimulus exactly the same from one to another, then the response is not. So there is variation both in amplitude and latency. Not even the simplest ERPs, which we can say, for example, somatosensory evoked potentials, where you are giving electric stimuli to the wrist, even those, they don't stay the same from one to another. So there are small variations. But luckily, if you are making an average about 20, then all the now 20, the next 20, and so on, they are the same. And that, I think that's good. And even the grand averages, if you're averaging over subjects, if you, for example, measure something and you have, for example, 60 subjects, and you can pick 20 and 20 and calculate the average of those. And if you have done everything properly, then the averages are the same. And I think that's one of the good things in event-related potentials. If they weren't, then publishing would be very difficult. You have to rely on that. Okay, requirements for a successful ERP recording. And I think the most important thing is, after the basic things, that you are preparing the electrodes or skin electrode contacts well, so that there are no extra resistance there, no artifacts out from outside the patients, for example, from the power line system. After that, it's important that you eliminate the slow artifacts, electrode and other artifacts. That's important. Fast artifacts you can usually filter out with low-pass filtering. But slow rhythms are more difficult because they are actually in the range that you are interested in, what you are recording. You can't filter those out. And with eye movements and blink artifacts, there is a special problem that they are very often time-locked to the stimulus. So if the patient or the subject has a task, for example, to press a button, then the blinking, let's say it's quite common that there is a time lock to the button press to the blinking, or any other. Sometimes patient or subject may actually, for example, see that now I saw the stimulus, now I can blink, even though she or he doesn't think that he's doing that, but it may be the thing what happens. So it's important to take a special care with the elimination of these eye movement artifacts. And in linguistic ERPs, this is sometimes forgotten. And I have here an example. In this paper, the authors say that trials that are characterized by excessive EOG artifacts were rejected. But it doesn't look like that, and I've put the red arrow there in the in the picture it shows the frontal channels there, and you can see that the amplitude, ERP amplitude, at that, for example, this FP1 or FP2 channel frontally is about 10 microvolts, and that doesn't come from the brain. There's no way that it comes from the brain, so it must come from the eye movements. And you should, when you are reading papers, and hopefully the authors show the original pictures of all the channels, and then it's a good way of looking at the frontal channels, where the signals go, and if they go at 1 second, if they go far away from 0, then it is almost certain that there is an eye movement artifact. And even the authors compared, let's say, between two conditions, and both conditions produce about the same kind of change frontally. It's still not good, because it means that they have not taken care of the artifact, and it may show itself somewhere else. And this is actually a paper that is telling about the P600 component, which I think that, at least with this paper, I don't believe that. I should do the analysis myself and then think about it. But is it there really, or isn't? So be careful with this kind of thing. If you are doing analysis yourself, you should learn to, for example, to correct for the blink artifacts. Because if in this case, for example, they were rejecting the artifacts where there was a saying and probably doing something, but if you reject the one sweep where you see it, it's not enough, because there is a baseline shift in the next one, and that's probably what's the cause of that, so that it stays in the next one and produces that kind of artifact. So, but this is a warning. Yeah. Okay, easier for me to close that. All right. I'm not meaning that you shouldn't read any papers. You should read papers. You should read the papers carefully. And don't believe anything.
Don't refer to my paper.
No, it's I'm maybe slightly pessimistic with this one, but I have the opinion, because I think because I have done so much other ERP work, and then when I started reading these linguistic papers, then I thought that they are not careful enough with the eye movement artifacts.
This tells you something about the present day state of sociology, of science. You have to publish a lot, and there are very many publishing venues, and lots of SHIT gets printed as well. So there is good science and bad science. How to tell them apart?
But I think this paper is...
Yeah, it's very difficult.
Yeah. But I think this paper may belong to the good part, but still it's not that good.
And we have to remember that EEG technique, it is quite cheap compared to MRI technique. So many departments have their own ERP equipment. So many students are doing that. Many people are doing that without maybe no knowledge of what they are actually doing. So it's because of equipment is so cheap compared to MRI.
That's right, yeah. But with MRI you can't do this kind of stuff, because the time resolution is not so. You can't do this kind of work with MRI. You can do with ERPs, or with EEG, or with MEG. So those are the ways of doing that. But I think things will improve. They'll always get better. And of course, this is not this eye movement artifacts. It's not so dangerous for the early components. It's more dangerous for those that happen after, for example, 500 milliseconds. Okay. Where am I in time? Well, I present some examples of ERPs, and I start with the first one. This is Contingent Negative Variation, or CNV. This was one of the, or probably the first event-related potential that was described. And it is a slow negative shift which develops between, or in the interval between two stimuli that are presented one after another. And the first one is so-called cue or warning signal, and the next one is imperative signal or stimulus, and you have to respond to the imperative signal. And the amplitude of signal is affected by expectancy. And that is why it actually got the name, the contingent, because there is a statistical relationship between the warning and the imperative stimuli. And this picture shows the case. This is from the original publication, which is from 1964. And it was in Nature, so it's fairly good. Good paper, even though after this was published a few years later, one author actually showed that part of this CNV actually arises from the eye movement. So but still it is a real thing. So there is the warning stimulus. In this case it was a click, and the imperative stimulus was a flicker of flashes after one another, and the patient then had to terminate the flickering light by pressing a button. And you see in the A figure there is the response to the click, in the B there is the response to the flicker, in C there is a response to click and flashes but with no task, and in D there is a task where the patient has to press a button and stop the flashing. And you see the negativity, that very quickly, actually the negativity increases after the click and then goes down when you press the button. And this is the CNV. For me this is an important, there is a physicist in the list of these authors. The second name is Ray Cooper, with whom I met actually in Oxford 23 years ago, and he bought me a pint of Watford 6X, which is an excellent British ale, in the King's Arms pub. So if you go to Oxford, you should, yeah, if you go to Oxford, you should go to King's Arms pub and have a pint of 6X. So it's very good ale.
This was a little commercial break.
And by the way, in the typical businesses, this negativity is it's upside down. As
Oh yeah, I forgot
in imaging is, I mean, left is right and up, right is left and up is down.
Yeah, I forgot. Yeah, I forgot to tell you. In most of the, let's say, signals of neurophysiology or psychophysiology, the polarity has been reversed.
Yeah.
Not all. There are some that it's in the right way. But with these ERPs, it's usually this way. But you can see it also the right way, the physical way. But mostly they are presented like this. Okay, then another example. This is mismatch negativity. It's actually a Finnish invention because it was first described by Professor Risto Näätänen in 1978. And then the psychology department of Helsinki University has been studying this a lot, very much. Also some other departments of psychology in Finland has done quite a lot of work with this one.
And now across the world.
Yes, but still, yeah. So many doctor's thesis has been made from this bump. Some people actually call the science bumpology, which is a good name. Yep, but mismatch negativity is an EEG response component that is elicited by deviance or deviations within a structured auditory sequence. And it is recorded using a so-called oddball paradigm. And that means that we have a pseudo-random sequence that consists of for example, two different tones, and these are presented to the patient. And about, or let's say most of the tones, for about 85% of the tones are so-called standard tones, and about 15% so-called deviant tones. And the subject must direct his attention as completely as possible off the tones, so that subject must ignore them, so not to listen to the tones. So they should be in the background. If they aren't, then it's not a real mismatch negativity what you are recording. So that is the paradigm. You have standard, so these bars there, those light blue bars depict the standards, and the deviants are the slightly reddish bars. So that means that how they are presented, so that they are short tones about 100 milliseconds length, and they slightly differ slightly in the frequency. So the standard tone can be, for example, 1 kilohertz, and the deviant tone frequency, for example, 1100 hertz. And the tones are presented with 1 second intervals. With that or shorter, you can also use shorter one. And you get the response then. Usually a frontal maximum. This is something that I have recorded from myself. These are group averages. And the shaded area there between the standard or between the deviant tone response and the standard tone response, that is the MMN. So you can say that it is usually you're using the difference curve and then define the area or you can define the peak where it is maximum. So this is something that I have used quite a lot in clinical work, or studying different patient groups, or mostly with that. And it's quite good if you are studying, for example, the dementia patient, but you have to do it slightly differently from the normal recordings, because you can't use a small difference in the tones. With, say, normal young people, you can use a very small difference between the tones. For example, if you have a kilohertz, and so meaning 1000 hertz, then you can have, for example, 1020 for the other, for the deviant. But with dementia patients, they don't hear the difference. They don't notice it enough, so that you can't use it in the same way. And this MMN reflects the pre-attentive discrimination of two different tones, or automatic change detection in the auditory world. So it's automatic, that's the important thing. And it has some properties that suggest that it's related to echoic memory, or the phonological loop. Do you know the phonological loop? Yeah, most of you, not all. It's the loop that is well developed in married men who use it for playing back the words that their wives are saying. After when the wife said that you didn't listen at all, then you use the loop to bring back what she said. And I think that if we actually did a study to measure the difference between married men and bachelors, it would probably show a real difference. Because if we believe that...
So being married gives you some advantage?
Yeah, I'm not sure if it is an advantage, but I think because our brains are so plastic, it must happen. But I'm not sure if it really happens like that. But that's the phonological loop, in my opinion.
The parrot loop.
Yeah. So the MMN actually disappears if the interval between the stimuli is increased to about 10 seconds, so that then you don't see MMN. It has been also used as a neural marker of language development. In Finland, for example, quite a lot of studies have been done to small children, and for example, the infants discriminate different phonemes before the age of 8 months. 4 months, actually, age of 4 months.
And isn't it the case that preterm infants can detect difference between acoustic signals as such and between those being uttered by the human vocal apparatus, phonetic versus acoustic?
Yeah, I think so too. Yeah.
I think Mary Jory at Turku saw that. So we are linguistically tuned already in the womb. That's a big thing.
Yes.
We make a difference between acoustic and phonetic.
Yeah, that's true.
Stimuli.
And there's been also, MMN has been used to show that why the Japanese children actually lose their ability to hear certain phonemes before the age of 1 year, and then in adults they don't perceive the things, and it makes it very difficult, for example, to learn to pronounce correctly some English words. Okay, a few words about linguistic ERPs. I did a PubMed search a few days ago, just by looking for the the union combined linguistics, one word, and event-related potentials, and actually it gave about 150 articles, so quite a lot. But I think it's probably not all in that, probably more. But even with this simple search, the number is that high, meaning that quite a lot of people are using ERPs in linguistics. And I have taken a few components here to mention separately, which is first the early left anterior negativity, which is the quite early component from about 100 milliseconds to 300 milliseconds. And this, or let's say the phrase structure violations are producing this component. For example, if you are saying that to the city, or the to city, or to the city, yes, produces this is one example. Of course, but with all these linguistic ERPs, there are usually many different things that are producing the response. This N400 is the one that is, let's say, probably the most studied, and the one that actually it's very easy to see in any kind of modification of the stimuli. It's usually from 200 to 700 milliseconds, so quite a long time interval where you can actually see it after presentation of word. It has a central parietal maximum, meaning that the maximum is somewhere there. So sensitive to many linguistic factors. And there is a fairly recent review by Martha Kutas and Federmeyer. So if you are interested, you should read that. So it has also other things than the linguistic things in that. Because Kutas has been doing quite a lot of work with N400. So I think it is a good piece to read. Okay, but then I'll go to our own example. Not yet. So this is something that we have done together with Jussi and Santeri and some people from Kuopio. So this is about the effects of number of stem allomorphs on ERPs. And we had a stimulus material that actually consisted of I, meaning E in Finnish, I final productive inflectional nouns, and the same number of unproductive inflectional nouns. Also we had I final pseudo words and A final nouns from two similar inflectional types or groups of.
Now somebody might ask, what is productive versus unproductive? It's the case that in Finnish inflection you don't have the difference between regular and irregular. Everything is irregular and regular, or the other way around. So we have productive and unproductive paradigms that compete with each other for historical reasons. So.
Yeah. And Santeri did the word list, which I think is very good. So the matching between the words. But really, the difference is really there that we are studying, not any other dimensions.
He will be thanked in the acknowledgement.
No. Santeri is the first author of the paper that will be published very soon.
Oh.
Yes, but we had a list like that, and then the subject had a task to press one button for each real Finnish word and another button for each pseudo word. And then we even changed the hands in the middle of the experiment. And our hypothesis was that the processing of unproductive words, which have more stem allomorphs than the productive words, that their processing is faster, meaning that the reaction times are faster, and the P300 that we see in ERP, that it's also faster, and that is due to statistical facilitation in these multiple processing routes. And the basic thing in statistical facilitation means that if you have two separate routes, then you get the result from the one that is first ready. And if they are originally, if you have one, let's say, then we have a case A where we have only one route, which has the same average speed, and then we have a case B which has two routes, but the same average speed. But if you always pick the one that is faster, then the average speed in the B case is faster. And that is the statistical facilitation in simple words.
And the basic idea about this is that it actually rests on the predictions and results of Mieni Järvikivi works on a Finnish model of inflectional production, reception. These unproductive paradigms, they have more stem allomorphs, and we have proven through the years that more of these stem allomorphs, like, let's say, foot, feet, that kind of situation, where you have e-umlaut kind of things, and they are sort of memorized, and they each act as an access code. They are access codes of the lexical entry. And unproductive guys have more allomorphs, therefore entry access codes than the productive ones who typically have one, or two only. These guys can have as many as 4 or 5. So they have lots of roots kicking each other's asses towards the lexical decision process. I am a finished way. That's the main point. So the paradox is, the more input roots you have, the faster your brain is. It's paradoxical, but that's the way this guy works. The more stuff is knocking, and the more doors that you get knocked on, the faster you operate. So the loner rules is the sort of competition, time-wise.
Mm.
That's the main thing.
Yes, and that's what happens time-wise, but in the energy-wise, then when we are using more routes, then we could predict that the processing of unproductive words requires more brain energy, because there are several routes going on there, and then of course they need more energy in that. But then we try to show that also. So those are the hypotheses. This is actually a case matrix of this, an example of this I-final words, and the vesi there, the upper one, has many different stems. You can see that this is vet, vede, vete, ves. So it has 4 in that. And the lasi, for example, there it has only 2. So it's lasi, 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 lase, lase. so meaning less allomorphs. And that's the productive case, or an example of a productive case. And this is in my opinion, this is the best picture in our paper, because I've done quite a lot of work and it's very difficult to get signals like this. This is actually a grand average global field power curves for words and pseudo words. And the global field power is actually a standard deviation of potential of all scalp electrode locations. You can call it with another name, for example, the linguistics group in Cambridge has done some analysis, similar kind of analysis, that they call it root mean square. That's also what it actually is. It's the same whether you call it global field power or root mean square. But anyway, it is the standard deviation of potentials. And the main thing is that it reflects the strength of the total brain activity as a function of time. It's not exactly that, but it reflects that. And it would reflect even better if you were able to measure from all over the head. Now I'm mainly recording from the top of the head and from side. So if we were able to measure, let's say, from below the brain, it's not so nice to place, for example, through your nose, throat something there that would lie close to the brain, but I think it might help in some cases. But the main thing with that curve is that they overlap almost completely. There are two parts where they differ. The first is about 100 milliseconds, which is very early, meaning that this must be related, somehow related to perception, or at least very early part of the word processing. I think it's not word processing really, that it arises from the fact that we have just seen the real words. We have a sort of memory images of them already, and they are different from those pseudo words that we haven't seen, and that might produce the first part of difference part there. The second one there is then later, and this is where actually the N400 is. So I think that's partly arises from that. But of course we can't speak now from N400 because this is not. It's always positive when you are doing the global field power analysis. It's always positive, but it tells you that there are differences somewhere there in the signals, and big differences because they're statistically different in that time range. And one good thing is also that it doesn't rise in the end, so that means that it's going downwards in the end, meaning that the energy is, there's always some artifact in that, but if there would be eye movement artifacts, it would go high up in the end there.
By the way, Ari, if this 100 milliseconds then is pre-lexical, pre-phonological, meaning visual, then it should disappear if we use visual forms written with different typographic.
No.
Wouldn't it?
No. It still could be visual. I think it is.
It would stick there?
Yeah. It depends on the definition what is visual. Is visual memory visual or yeah? Because I think visual memory is part of the visual. And then if it wasn't, then you would be right.
I'm trying the same stuff.
Yeah.
Sort of
but we are not discussing about this part yet. it is interesting. I think it is very interesting part. Yeah, and we will, yes. But the later part is. But the basic thing is that it's very good. It would be difficult to produce two curves that would overlap almost completely, except those 2 points. If you were trying to do that, it would be difficult. And this means that the matching that Santeri did has been very good. Yes?
Since we are educating people for the future, for us, this is too late. This is one piece of sort of observation for the fact that when you are teaching somebody what you have done, you learn a lot. Or when you are listening to somebody who's talking about your own experiments, you realize, wow, there's something that we still could do. So teaching is very good. Don't just do research. Teach people as well, because when teaching, you get ideas.
Yeah, that's right. That is right. Yeah, because when you're teaching, you have to think again.
Think about things.
Yeah, you have to think again. Yes. Yeah. Okay, but I think this is something nice. I've done quite a lot of pictures in my life, and I think this is the best one. Even though the reviewers in these linguistic papers don't like it, I think this is the best that I have ever made.
What are the bad ones?
No, not in this paper. Okay, but this is something also that I think there are only one group that has fairly consistently used this, and it's the Cambridge group. Use this principle of producing this global field power or this root mean square curves, and I think it should be made compulsory. You shouldn't be able to publish anything without that. If I were an editor of your main paper, which is, I don't know which that is, then you should force the people to do it, because it's not difficult. Almost all the programs that you're using are able to produce it. So it's not difficult to do, and it would tell so much about the quality of the recording. So I think it would be important. Okay, but let's jump to the next one. This is now, or these are curves for productive and unproductive words from one electrode, from the Z-set, which is the central, from the center of the head. And you can see that there is also a difference, a statistical difference, one part. But I think in this, it's probably more interesting this 40 millisecond that I have marked in there. It's the positive wave there in the red and blue curves. That's a P300 actually, compares to the, I haven't told you about, but it's one of the components that you quite often are recording, and it's related to the reaction time. And actually this reaction time difference that we got from the behavioral result, we're recording also the reaction times, they are about the same as this latency difference. So it goes quite nicely to that. But what about the difference between the productive and unproductive curves? Now I'm also showing the global field power, and you can see that as we assumed, or our hypothesis was that the unproductive is actually, you need more brain activity for that, then that goes that way. It's not statistically very strong, but still there is a part that is in one-sided test which we can do, because that was our hypothesis, that it's
there is a direction in our hypothesis. We can use a one-sided test. There is a difference, and also the average value for, have calculated the t-value from the rest from 300 to 600. The average t-value corresponds to a p-value that is below 10%, so that at least it's tentatively correct in that one. But you see that it's not as clear with this compared to the curves of the real words and pseudo words. And one reason is that there's so much less sweeps or these single responses in the average, because when we were comparing the words and pseudo words, then everything was there, but not in this one. This contains only a small part, and it increases the noise. So we actually would have been better if we had maybe 10 more. We had 20 subjects and maybe 10 more, and it would be even nicer. But it's not bad, and in spatial analysis it looks better than this. Is in the top row there are voltage differences, which is the productive minus the unproductive, and the projector is taking something out of that, but you see the main thing in there. So there is the biggest thing is the negativity, centroparietal negativity, like in N400, in the time points of 346 milliseconds and then 442. Those are the main things. And also the lower X, they show the p-values that were actually calculated for each spatial point. So that is and made to a picture, and you see that there is a very small p-value especially in the 346 millisecond in the central parietal, so meaning that it is N400 component. So that's where the most, or the biggest difference between the processing of these two curves or two different words is. Okay, I'll show you this one again. Go back to the one, this curve. You see that there are deflections in the productive and unproductive curves that are slightly in different phases, and you could think that maybe there are sub-processes, but of course this is not something that you could write in a paper. Very difficult to tell, but it looks like that it might be even there, the different roots. Yes?
Is there any difference in frequency of the words you used to test those?
Oh, they were matched in many variables. Such
Everything was matched.
Okay, because
yes, surface frequency, lemma frequency, gram frequency, and etc.
Okay.
Between two groups. Yes, we were aware about this.
Yeah, sure.
We read our psycholinguistic Bible.
Yeah, excellent.
Yeah, okay. But yeah, just in case.
Yes, you're right.
Okay, I think that's my part of today's show. But if you have any questions,
Have any questions,
or any comments?
I still have another one question. Am I right in understanding that this result suggests the difference in processing of the productive and unproductive words? If it is so, does this correspond somehow to the model, for example, proposed by Pinker in his words and rules models? I mean, in processing regular and irregular words.
Yeah, it's a dual route model.
Yeah.
Yeah, of course it is.
It is, yeah.
Yeah.
So that's what I was.
Because of course Pinker who got the idea to write it in science, and we didn't.
Okay. Okay. So that's more or less about the same thing.
Yeah, but it's at the meta level.
Okay.
It's the same
But
thing.
not exactly, because in Finnish language we don't have such a distinction between regular and irregular words.
At the meta level.
Yes.
I see.
At more abstract level, yes.
Mm-hmm. Thank you.
I still might add something about that, of that Finnish, because when I showed these curves between the pseudo words, or the stolopit power between the pseudo words and real words, there was almost complete overlap. And I think the Cambridge group does, in my opinion, it does very good work. And they have had bigger differences, which I think they may partly arise from the fact that English is, it's not so easy in English to separate. There may be more processes when you're separating real words and pseudo words than in Finnish. But that's the physicist's opinion.
And not then this, our productive and unproductive guys are actually fighting for the same solution space. They have the same endings. They look like potential members of the same paradigm. That's something that's different from the Indo-European regular versus irregular. Definitely. So, yeah. And I have done linguistics for 40 years, and one thing I've learned, languages are somewhat different. English is not Finnish, and vice versa.
We do have about 20 minutes for break.